I have posted the answer to the brain teaser that I had posted. It was supposed to be a week ago, and it's probably a couple weeks now. Um, I'm going to restate that very briefly. So the question is, if I take a volume of air, a specific mass of air, and I compress it 10 to 1, and I do that fairly quickly so that it's effectively an adiabatic process. I'm not losing heat during the compression process. If I do that, the pressure will go up in that vessel, the temperature will go up in that vessel, the pressure will go up by more than 10 to 1. If I then let that come back to ambient temperature, I lose energy as heat. And the question is, when it gets back to ambient temperature, how much of the energy that I used to compress it have I lost as heat? So I posted the very brief answer as a video, and I'm pointing to this video that gets into the much trickier business of how and why that works. The short answer was every bit of the energy I used to compress it gets lost as heat when I allow it to return to ambient. And I fully understand that makes me sound insane, which is to some extent the object. Like the downwind cart, it sounds like over unity, perpetual motion, and so forth, because I still have this compressed air that I can use to run my pneumatic tools, despite the fact that I've lost all the energy I put into it to do the compression. So the teaser is it's not energy in the gas in the strict sense. It's entropy that allows this to operate the way it does. And it turns out that entropy, every time I think I understand entropy, it turns out I don't understand entropy. And that makes this even more interesting to me. There's something more here. So for that, we have my physics spirit animal and mentor, Dr. Eric Michelsen, who's going to talk to us about entropy. And I'll mention too that there's been a lot of videos on entropy, and I think I've watched them all, and I've learned a lot. But I've also learned that most of them are in error. And it reminds me of my field is aero, and it reminds me of all of the explanations of how an airplane flies, and it's rare to get one right. So with that, Dr. Michelsen, maybe you can tell us a little bit about your background and what you're here to explain to us.
Okay. I started out as an electrical engineer. My undergraduate degree is in electrical engineering. I worked in industry as a practicing engineer for roughly 20 years. And then I went back to graduate school, got my PhD in physics, and that was in 2010. And I've been teaching physics on and off at the University of California since then.
And what do you hope to do when you grow up?
You know, I haven't really decided what I want to do when I grow up. I'm still working on that. And I'm on Medicare now, so I think I better get to, well, I really like this brain teaser because I think it provides, it's clever, it's astonishing, and it provides a really good vehicle for learning some real thermodynamic concepts. And I think those concepts are accessible to a lot of people. And so that's what I hope we can accomplish today, is to at least get correct ideas across that are sufficient to sort of make sense and get people started. And if people want to learn more about it, then there's lots of places, well, there's a few places they can go to learn more about it. And at the risk of self-promotion, one of those places is my website and my Statistical Mechanifesto, which is about thermodynamics and the statistical mechanics that underlie it.
Well, I have to say I was honored that you ended up including this brain teaser in that document, and that's a great document. The thing I like about this kind of brain teaser is I really like brain teasers that are very easy to pose, that anyone can understand the question, and that almost no one will have the correct intuition to get the answer right, but that hopefully it's understandable once explained properly. So if you are able to make it clear to me, you will have accomplished a great deal.
Okay, so in fact, let's jump right into it, because I think we can get to the heart of this in just a minute or two. We can get to the heart of what's going on very quickly, and then we'll expand upon that basic kernel truth, I hope. So first off, this is clearly a thermodynamic question, and before we talk about entropy, important to recognize what is a thermodynamic system? What does that mean? In other words, when is entropy important? When does entropy matter for the understanding of a physical situation? And a thermodynamic system is a system where heat is a significant part of its operation. I mean, that's just a simple definition. So for example, if I want to analyze an electric motor and its efficiency, probably the heat isn't going to be much of a factor. And at most, maybe I put a fan on it to blow it off and cool it, but that's not really the fundamental essence of how it works. And so heat is not a significant part of an electric motor's operation. And normally we wouldn't call an electric motor a thermodynamic system. Now, the brain teaser you pose is clearly a thermodynamic system because it involves compression and expansion of gases and heat exchange with the environment back and forth. So if we're going to talk about entropy, we need to make sure we're actually talking about a thermodynamic system in the first place.
So let me, if I may, you just gave a good definition of what a thermodynamic system is. And I know we're going to get into a lot of detail on what entropy is and how it works. Is it possible to give us, as the teaser, is there a one-sentence definition for what entropy is? Or a short definition?
There is a short definition, but it won't mean much until we expand on it. But I'll give it to you anyway, because we're gonna start there. And the short definition is, given a system which we choose some constraints for, we choose some conditions that define our system. Given that system, there are usually many, many different microscopic ways that that system can exist. If I have a box of gas in front of me, that's my system. I can say it's at a fixed temperature and it's a fixed volume, say. But there are billions and billions of ways that the gas molecules inside that can be arranged. And entropy is just the number of ways that the gas molecules can be arranged and be consistent with the constraints that we have imposed on the system. And that number of ways is called the multiplicity, and it turns out that it's usually more convenient to work with the logarithm of the multiplicity, and we call that the entropy. So entropy is really just a measure of the number of microscopic states that are consistent with the macroscopic observable properties of our system. The states are absolute and countable because they are quantized. And so because of quantum mechanics, we can literally count them. And even with 10 to the 20th molecules, we can figure out exactly how many quantum states those molecules could be in. And the logarithm of that number is the entropy.
When you talk about the quantum states, you're actually talking about the finite number of positions, locations that a particle can exist in. Is that included?
That's included. The only difference is that to define the state of a system, we need to know not only where the particles are, but we also need to know how they're moving.
Yes.
So we need to specify not only their positions, but their momenta as well, or equivalently, their velocity as well.
Right. So I'm just thinking, when we talk about the number of states, there's the number of particles, which is immense.
Right.
But then the number of positions that any given particle could take, it's got to be that's got to be in the trillions, right? Or far more.
Inconceivably large. And I have some quantitative numeric examples in my notes. But essentially, if you have a box that's 1 cubic centimeter and you put 10 electrons in it at room temperature, the number of states in that, even for the tiniest allowable fluctuation in temperature, is 10 to the 200. And so we're talking numbers that I don't believe the human mind can really comprehend. But one reason we take the logarithm of the number of states to give us the entropy is it turns inconceivably large and unmanageable numbers into numbers that we can get a handle on and that we can manage and calculate with much more easily. So that's one of the reasons we take the logarithm and call it entropy. It's not the only reason. So who cares how many states? Why is that important? And the real kicker is that in most thermodynamic systems, it sits in an environment. And in most of the time, that environment and its relation to the system is important. And in particular, the system and the environment can in this case especially, can exchange heat. They can exchange energy. Sometimes energy goes from the environment into the system. Sometimes energy goes from the system into the environment. And what regulates that flow? What determines whether energy goes in or out and how much? Entropy determines that. And that's how you can get energy out of seemingly nowhere. Is it's not really out of nowhere. The energy is actually coming from the environment, and it's being drawn in by the increase of entropy in the system. And so we'll do a specific example, I think, of an isothermal compression and the isothermal expansion, which is the simplest case. And we'll be able to sort of see this. Let me put you at ease, though. Energy is energy, and everything you have learned about energy is still valid. Energy is conserved, and energy is the source of work. And that's still true. Entropy doesn't change that. The trick is that entropy allows you to draw energy in from the environment and put it to good use. And so you're not fabricating energy out of nowhere. You're just redirecting the energy that's already there.
So let me ask you this. You said you're hesitant to use the term entropy gradient, and let me say what I meant by that, and then you can tell me whether it's wrong or needs some correction. My understanding is that inside our compressed air tank at the end of this experiment, we have a low entropy gas, relatively speaking, and outside we have the higher entropy atmosphere. The gradient I'm talking about is basically a step change in this case. And I thought that relative low entropy versus high entropy was what enables this to work as it does.
Well, so here's my concern with that is the environment is very large and the system here is very small. Say it's a syringe.
Yeah.
So the environment has much more energy than the system does because it's much bigger. The environment has much more entropy than the system does because it's bigger, and it always will all throughout the cycle. It always has many times the entropy that the system has. And the environment has much more free energy than the system does because it's so much bigger. So it's not really a direct comparison between whether the environment has more entropy or less entropy than the system. The environment always has, 100,000 times the entropy of the system because it's 100,000 times bigger.
What if I put this syringe after I do my compression and I let it cool? If I then introduce it into a vacuum chamber where there are no particles outside of it, will it still work? Can I still operate my pneumatic tools from that compressed air? And B, is there an entropy associated with a vacuum?
No, the entropy of a vacuum is zero.
Okay.
And keep in mind, when I say a vacuum, I mean no photons either.
Yeah.
I mean nothing. And because there's only one configuration, or really I should say there's only one state of a vacuum. And I'm not even sure it's well defined because I'm going to say in a minute that the entropy of a static system, it's not even zero, it's just undefined. It's not even a legitimate question to ask.
But the experiment will still work in a vacuum. Is that correct?
It will, but you have to be. We would probably have to reanalyze it because. So, for example, I think the easiest way to analyze this system is to actually do an isothermal compression and an isothermal expansion. That's the simplest analysis, and I would recommend starting there. But then it's very instructive to look at an adiabatic compression followed by a cool down, which gets you to the exact same final state and allows you to do the exact same expansion and recover the same amount of work. But that's a less efficient process. You waste energy doing it that way. And it's very instructive to understand the difference between those two processes. But in the simplest case, if we look at the isothermal process, if we do this in a vacuum, that's impossible. You can't have an isothermal process because you don't have a constant temperature environment to keep the temperature steady.
Understood. But to take it to practical terms, what I'm asking, if I perform the first half of the experiment as I normally do, in other words, I compress it, I let it cool, but then I take my compressed air tank into a mechanic's garage that happens to be in a vacuum. The entire garage, the car, the mechanic, everyone's in a vacuum. Can I still operate my pneumatic tools from that pressurized tank?
Oh, sure, absolutely. Because your
Okay.
molecules still have kinetic energy. The molecules are still at a finite temperature. But
Yes.
as you operate those tools, the temperature of your gas is going to go down because now
Yeah.
you're taking the energy out of the gas itself, and there's no environment to help you out.
And by the way, I think I agree with your point about analyzing an isothermic system instead of an adiabatic, and it's one of the reasons that I posed it as an adiabatic system.
Oh, okay.
But well, go ahead.
I think actually, if you really want to understand what's going on, you should understand both.
Yeah.
But it's simpler to interpret and describe the isothermal one first. And then it's a little bit more complicated to describe the adiabatic process. For one thing, it's a two-step process. There's
Yes.
adiabatic compression, and then separately now there's the cooling down back to
For the purpose
ambient
of
temperature.
understanding, I completely agree with you. For explanatory purposes, that's absolutely the way to go. For posing something that sounds insane, I like
Yeah.
the adiabatic approach.
Yes,
In any case.
absolutely. And I totally agree. I mean, in a sense, a good part of some puzzles is they actually include some things that in the end don't really matter, but they feel like they should matter. And so that makes it the more puzzling. But there is a difference now because when you do the adiabatic process, you actually waste some work and you put in more work than you get back. When you do the isothermal compression and expansion, you waste nothing and you get back exactly the work you put into it.
Okay.
So, but it's still worth understanding how that comes about. Because keep in mind, in both processes, the final compressed state is exactly the same. No matter how you get there, it's the same final state. It has the same internal energy. It has the same entropy. It has the same free energy. All of those are state functions, and how you get there doesn't matter.
So in a few sentences, how is it possible that after I've compressed my gas and for the moment adiabatically, and I've driven it to a higher temperature, and I've now lost all of the energy as heat, all the energy I put in, I've lost as heat as I let it cool. How is it possible then that gas can still operate pneumatic tools?
Right. And the key to that is that as the gas expands, its entropy increases. And in a constant temperature environment, when entropy increases, it draws heat energy from the environment. And so the energy to operate your tools ultimately comes from the environment. But entropy is the mediator that pulls that energy from the environment and feeds it into your power tools.
So it sounds very much like entropy has a potential energy associated with it, and yet it doesn't. How is that possible?
So it's not literally potential energy, but it has the potential to draw in heat energy, which is real energy. Heat energy is real energy, just like any other energy. And so that's the key to how entropy gets stuff done, is it doesn't have energy of its own, but it has the ability to direct the energy of the environment and the energy of the system. And in particular, in a constant temperature environment like this is, when the entropy of a system increases, it necessarily draws heat in from the environment. There's no choice. It has to. If your entropy goes up, the heat gets drawn into the system. But conversely, when your entropy goes down, heat gets pushed back out from the system into the environment. And that's why when we compress this thing, we put energy into it. Initially, in your adiabatic case, the temperature went up, and so the entropy stayed the same. Adiabatic is isentropic, that is constant entropy. But then when it cools down, that means heat is flowing from the gas into the environment, and its entropy is going down. When the entropy goes down, that heat energy is forced out into the environment. But in a sense, it's kind of like a potential energy store. Even though the heat got shoved out into the environment, it doesn't mean it's lost forever, because if our system entropy can be allowed to go back up, it'll draw that heat energy right back in. And so in a sense, the entropy allows us to use our environment as a storage of heat energy.
And if I allow that gas to expand slowly, that's exactly what it will do. It will draw the heat back in from the atmosphere. And I think you've explained to me that if I allow it to expand very rapidly, it doesn't have time and it won't draw the heat in from the atmosphere. Instead, it will itself get cold. The gas that is doing the work will get cold in the process.
Right, that's exactly right. And that's similar to what happens if we were to compress it, put it in a vacuum, and then let it expand. Either way, it's not getting heat from the environment. And so the only source of energy is in the molecules of the gas themselves. And if they do work, they're going to get colder. They're going to slow down.
Now, when you talk about the energy associated with entropy, drawing in heat and moving heat out, I think about the order of a deck of cards and the entropy of a shuffled deck versus a deck as it comes from the factory in order. And I can't figure out how changing its order or having two different decks in two different orders can be associated with energy.
Okay, so that's a very good question. And it gets right to the heart of what is a thermodynamic system. And our definition of a thermodynamic system was that heat, and really that means random energy, is a significant part of its operation. And that definition of a thermodynamic system really precludes us talking about the entropy of a static system, some static macroscopic system, like a deck of cards or a pair of dice or a bunch of coins, because they're not dynamically changing states. They are not thermally agitated generally. If it's just sitting on the desk, it's a static system. And so it's not swirling through trillions and trillions of microstates. It's just stuck in one single fixed static state.
So that tells me that that's not a thermodynamic system. And I think you're telling me that means that it doesn't really have an entropy associated with it.
That's correct. Now, there's a way we can allow a precise definition of entropy, and that is to be careful how we define what we mean by what we're asking the entropy of. And so our definition of entropy is the number of ways that a system, the number of microscopic ways that a system can satisfy some given constraints. So it is, in this sense, it's meaningful for me to say, what is the entropy of a shuffled deck of cards? Well, a shuffled deck of cards can exist in 52 factorial different ways. That's a lot of ways. So the multiplicity of a shuffled deck is 52 factorial. And then its entropy is going to be the logarithm of that. And usually we multiply it by a scaling factor as well, the Boltzmann constant. But the essence there is the logarithm. So what we can say is the entropy of a shuffled deck of cards, which is a specification of conditions, that's a legitimate thing to say the entropy of. What's not legitimate is to point to an actual specific pack of cards and say, what's the entropy of that thing?
I see. So you're talking about a category shuffled deck of cards, because
Right.
that category could be 52 factorial possible possibilities, as
Right.
opposed to the deck that's sitting on my desk that
Right.
is exactly one order.
Right, that's right. And this might seem contrived, but actually this is how, in real thermodynamic theory, this is how we can define the entropy of systems that are not in equilibrium. We specify the conditions of the non-equilibrium, and that allows us to assign an entropy to it. And without that kind of definition, we wouldn't be able to even talk about the entropy of anything that was not in equilibrium. Well, the fact is the whole universe is not in equilibrium, right? Nothing's in equilibrium. I am hopefully very much not in equilibrium with my surroundings.
Yeah.
If I am, I'm dead. So it actually becomes important. And it also then allows us to illustrate legitimate concepts of entropy and to apply the concepts of entropy to macroscopic systems like cards and dice and coins that people are very familiar with.
I think that helps me a little bit with my question of whether entropy is a a human construct, I'm going to say like mathematical algorithms versus a real world thing. And the fact that this business of it being a category of deck of cards, that feels more real world to me. And certainly the fact that entropy can cause experimental results. That's a real thing.
Absolutely. And your brain teaser is one example of that. An entropic spring that can lift a weight is another example of that. It's not only a real world effect, it does real world work.
So when I compress a spring, the energy I've stored in it, the potential energy is 1/2 kx squared, where k is the spring constant and x is how far I compress it. When I compress the air in my syringe, it feels a lot like a spring. I get this sort of sensation of 1/2 kx squared. I can let it expand. But I think you're saying they're fundamentally different things. The potential energy in a spring is not related to the entropy, or is it?
No, you're right the first time. They are fundamentally different things. And the potential energy in a spring is very different from the potential to get work out of a gas. So potential energy has a precise physical meaning. When you compress a spring, actually, if you look microscopically, all that energy is stored in the electrostatic repulsive energy of the electrons in the atoms of the spring. And entropy is not a factor there. Heat is not a factor there. You can compress a spring in the dead cold of winter and it works just as well. So it's not a thermodynamic system. Entropy is not a consideration. In a gas, if we talk about true potential energy, and by definition, an ideal gas, there's no interactions, there's no energetic interactions between the molecules. There is no potential energy, but that's different from there's no ability to do useful work. We have an ability to do useful work, but we don't have strictly potential energy. And entropy is one of the quantities and moderators of this ability to do work in a thermodynamic system. But entropy only applies to a thermodynamic system. Springs and radio waves, we don't care about entropy.
Okay. Very interesting. So there's this talk of free energy. And can we distinguish free energy versus kinetic or potential energy?
Absolutely. So what we've seen is that entropy allows us to make use of energy in the environment to do useful work. When the gas expands, its entropy increases, it pulls heat in from the environment and does useful work with it. Wouldn't it be nice if we could calculate how much useful work we can get out of that entropy? Yeah, it would be. Well, guess what? We can. And what free energy tells us is how much useful work we can get out of a system, taking into account both the internal energy of the system itself already and the heat energy that's in the environment that will become available to us when the system operates. And so free energy is just the sum of two terms. It's the sum of the real energy of the system plus the energy that we can get out of the environment when we increase our entropy.
So something I think about with regard to this experiment is I imagine that I've compressed this air into a small volume. For the purposes of this example, it'll be a box. And this box is in a room of non-compressed air. And I imagine removing the walls of the box. Now, inside of what was the box, I have a bunch of particles, a bunch of molecules of air moving around at the same velocity as those that are outside it. The only difference between the air that was inside the box and outside the box is that there's more particles in that area. There is a higher concentration of energy, but every particle in the box has the same energy as it would, statistically speaking, as every particle that was outside of the box. Can we talk about the mechanical means that entropy exploits to allow us to extract energy from that system?
So that gets a little bit trickier because the actual mechanical means of this comes out of what's called the Boltzmann distribution. and it requires a little bit more detailed examination of the physics of what's going on. And in the end, though, a system or a combination of the system and its environment, an isolated system is going to spontaneously evolve to the state that's most likely, the macro state that's most likely. And the macro state that's most likely is the macro state that has the most number of microstates that are consistent with it. And that's the maximum entropy principle. Any isolated system will spontaneously evolve to the state of maximum entropy. And
so I thought your answer was going to be you can't handle the truth with respect to the mechanical explanation, but it sounds like you're getting there, and it sounds like the mechanical explanation is a statistical one. Is that fair to say?
Absolutely, and that's why it's called statistical mechanics.
Okay.
However, I would say, so statistical mechanics uses only a very small amount of statistics. A lot of people think, oh no, and they recall their statistics course, which was probably also badly taught. And you don't need any of that. You don't really care about 99% of that statistical stuff. The one thing we use more than anything is just the law of large numbers. That if you have a huge number of particles, then when you measure something, you're going to get the average value. And the probability of you getting anything other than the average value is negligibly small. And I mean like 10 to the minus 5,000. You know, it's negligibly small.
So that's kind of the business of saying that an ideal gas, if I have 100 moles of ideal gas in this room, there's some possibility that all of those molecules might be in the upper right-hand corner of my room, but it's not going to happen.
Right. And I mean, we're talking about, probabilities that it would never happen in a trillion lifetimes of the entire universe. It's just inconceivably small. And it's not a realistic possibility in any way, shape, or form. And so the laws of thermodynamics are as absolute and rock solid as anything you can imagine.
So it's certainly not possible with that attitude. Okay.
I mean, at that point, you'd have to start questioning the fact that quantum mechanics allows certain non-classical effects to happen as well. And they are equally, in a macroscopic system, they are equally unlikely to occur. But, the only reason we have physics is because that stuff never happens and we can predict the outcomes of experiments. I did want to mention one more thing, though, about entropy. When we're trying to visualize entropy, probably the most common visualization I hear is one of disorder. And I really don't like that visualization. And I think it very often will mislead you. And a much better visualization of entropy is uniformity. Uniform systems have high entropy. Non-uniform systems have low entropy. And it's more than that. But your previous example of imagine we have this box of compressed gas inside a room, and now we pull the sides of the box away. And for a short time, we have a higher density of gas molecules here where the box was than we do in the rest of the room because the pressure is higher there. So that's a very non-uniform distribution of the gas molecules, right? There's two, by the way, in the middle.
The pressure is higher, just to clarify, is just another way to say there were simply more molecules in that volume, not that they're moving faster.
Absolutely. The reason the pressure is higher is because the molecules are hitting the walls more often, but they're not hitting the walls any harder.
There are simply more molecules to hit the walls from the inside.
Exactly. That's right. So initially, when we pull the sides of the box away, we have a lower entropy situation than we will later on when those molecules diffuse out into the room. Because initially, when they're concentrated in the middle, that is a non-uniform distribution of molecules. So I'm only offering this as a visualization aid to help people think about things and to help people make intuitive judgments about what might be higher entropy and what might be lower entropy. in the end, if we want to talk about the entropy of the room with this higher concentration, we have to define a precise and unambiguous set of constraints that defines the condition of the room and all the molecules in it. And only then can we speak precisely of what is the entropy of that set of conditions, of that set of constraints. Because the only thing that has an entropy is a set of constraints. And then we can answer the question, how many microscopic ways will satisfy those constraints?
So what more can you enlighten us with on this business of entropy and what we as concerned citizens can do about it?
Well, maybe the next step at this point is to actually consider the isothermal compression process, the isothermal expansion process, and then do it again with the adiabatic compression and cool down, and we can see the difference. And I have calculated all the actual quantitative numbers for this in kilojoules and in joules per Kelvin for a realistic compression example at room temperature for realistic amounts of gas at realistic volumes. Just so, and I calculate the relevant quantities at each step of these processes. So if you want to get a more physical sense of what's happening, this includes all the numbers. And at each stage, though, I describe what the numbers mean physically, like what's going on here. So in the isothermal case, the only way you can be isothermal is you have to compress very slowly, because at every moment, as you compress a gas, it's going to tend to want to increase its temperature because you're putting work into it. So you're increasing the internal energy. If you compress it slowly enough, we can keep that temperature rise arbitrarily small.
Now, couldn't I theoretically do that more rapidly if I put my syringe in a water bath and I control the temperature of the water bath so that I can basically suck the heat out at such a rate that I keep the internal temperature constant?
You can do it faster in a water bath. In any realistic compression, no matter what, there will always be, in principle, some finite temperature rise. The key here is that we're saying that in principle, we can make that temperature rise as small as we want, as small as we have patience for, because this, no matter what, the slower we compress it, the smaller the temperature rise will be. So if you come to me and you say, I want you to keep it within 1/10 of a Kelvin, I say, okay, I can do that. But then if you come back and say, no, I want you to keep it within 100th of a Kelvin, well, I can do that too, because I just have to compress it 10 times slower. So you're compressing it, the temperature rises by an infinitesimal amount, which facilitates a heat flow then from the infinitesimally warmer gas out into the environment. And by compressing slowly enough, we keep that temperature difference as small as we want. And what that means is that the entropy of the gas is going to decrease because its volume is decreasing. And so there are fewer ways for the molecules to be arranged in a small volume than there are ways for the molecules to be arranged in a large volume. So if we count the number of ways we can satisfy the constraint of a small volume, it's certainly going to be less than the number of ways we can satisfy the constraint of a large volume. So the entropy is going down. The energy is staying the same, so the molecules are all moving at the same speed, as you noted earlier. And what happens, though, we can actually calculate quantitatively how much does the entropy of the gas go down. And we can calculate quantitatively how much does the entropy of the environment go up. And as long as they stay at essentially the same temperature, those exactly balance. All of the entropy that's lost by the gas is gained by the environment. And there's an important quantitative property that we have to be aware of here, which is that the environment is large. And so its temperature in principle goes up by a tiny bit, even if you dump some heat into it, but it's much, much larger than the system. And if we, by choosing a large enough environment, we can keep the temperature rise of the environment for any amount of heat that we care about arbitrarily low, arbitrarily small. So a key factor here, though, is that the temperature of the environment does not perceptibly change, but its entropy does. Its entropy goes up by a finite amount. So its temperature goes up, of the environment goes up by an infinitesimal amount, but its entropy goes up by a finite amount. And you can calculate really easily that the entropy lost by the gas is exactly the same as the entropy gained by the environment. So that's called an isentropic process, meaning constant entropy. And now we're talking about the net entropy of the environment plus the system is not changed.
And that's in the isothermal compression case. And
Right.
that is not true in the adiabatic compression case?
It's not true in the two-step case.
Got it.
In the first step of the adiabatic case, the entropy of the gas does not change at all, and neither does the entropy of the environment change any at all. But then in the second step, so we should do the whole thing. If in an adiabatic compression, you do the adiabatic compression, which means there's no heat flow allowed. So you insulate it very well, or you do it very quickly, but there's no significant heat flow. And you can show that entropy is related to heat flow and temperature, and with no heat flow, there's no entropy change. So the entropy of the gas does not change, and the entropy of the environment does not perceptibly change. But now your gas is hot because you did work on it, and it didn't lose any heat. So its entropy is the same, even though its volume is smaller, because it's hotter, right? So smaller volume means lower entropy, higher temperature means higher entropy, and in this case, those two effects exactly
balance.
Correct. And there's no net entropy, there's no entropy change of the gas at all. It's zero. But now we have to let the gas cool down. And this is where we have a net entropy gain of the system plus its environment. Because if you work it out in the numbers I use, the temperature of the gas goes up from 300 kelvins to 396 kelvins, almost 400 kelvins. By the way, that means you had to do more work to compress the gas, because at a higher temperature, the gas has a higher pressure and you had to fight it more. So the adiabatic compression takes more work. And in my numeric example, it takes about 15% more work to compress the gas adiabatically than it does to compress it isothermally. In the adiabatic compression, we compress it. The temperature has gone up quite a bit. It took more energy for us to compress it. Now the internal energy of the gas is higher than it was before because it's hotter. Yeah. It's almost 400 kelvins now. And now we let it cool down. Now we've got something going on, because now we have a hot gas at almost 400 kelvins, and it's bleeding heat into a much cooler environment at 300 kelvins. That means that the entropy lost by the gas, or the entropy gained, I should say, by the environment is more than the entropy lost by the gas. And so the two entropies don't cancel out. And in fact, the entropy, in my example, the entropy of the environment goes up by 267 joules per Kelvin. The entropy of the gas goes down by only 231 joules per Kelvin. There's a net increase of the system plus environment of 36 joules per Kelvin. That costs us work. Anytime the net entropy of the system plus the environment goes up, you have wasted an opportunity to do work.
So I want to put that in real terms. I believe what you're saying is that if I build a compressed air powered car, so I compress my air, I put it in a tank in the car, and I run my car on that, I would be better off doing both an isothermal compression and an isothermal expansion in terms of the efficiency of my car. If I compress it very rapidly and let it cool down, I still have my free energy that I can do work with, but it's going to be, the free energy now is going to be significantly less than the energy I expended. And those two don't have to balance out. The energy I expended is lost as heat. The free energy that I have now to do work with, it does not have to be as much as that first amount of energy. Is that fair to say?
Well, if you compress the tanks so that they end up in the same pressure and the same temperature, then their free energy is the same.
But, very good point.
But if you compress them rapidly, you had to do more work to do that. And now you've wasted energy, because when that thing cools down, that work is going to go out into the environment and you are never going to see it again.
That's a very good way of looking at it. When like I say, I first did my numerical analysis on a 3000 PSI system, and then I decided 10-to-1 was a better one for posing the problem. And I was astonished at how much energy you're putting into that 3000 PSI system. I believe it came back down to 1200 PSI when I let it come back to ambient. So it doesn't lose a few percentage points of pressure. It loses the bulk of it.
Yeah, a lot. And by the way, in my numeric example, for illustrative purposes, I only did 2 to 1, and that's why my loss was only 15%. A realistic system would be much, much more than 2 to 1, like you say, 10 to 1 or 30 to 1. So in the adiabatic compression and the cool down, the reason you end up in the same state, you can do the same amount of work, but you had to pay more work to get in that state.
Yes.
And in my example, you end up losing basically 10 kilojoules of work. You have to do 10 kilojoules more work to compress it and cool it down, and you never get that work back.
So in the isothermal process, I lose energy as heat. In the adiabatic, I lose much more energy as heat. And that difference is the lost energy in terms of the efficiency of my process to do work after the fact.
Right, because in the isothermal process, you lose energy as heat, but you're going to get it back again when you do the expansion. In the adiabatic compression, you lose more energy as heat. You're going to get some of it back when you do the expansion, but you're not going to get all of it back.
I'm only going to get back what I would have gotten if I had compressed it isothermally.
Exactly. We summarize what we've said here. We've said that a thermodynamic system is a system where heat is important, where heat is a significant part of it. We said that entropy is a count of multiplicity, the number of ways that some constraints can be satisfied by microscopic states, the number of microscopic states that satisfy those constraints. That's the definition of entropy, but the significance of entropy is that entropy controls how much and in which direction the heat flows. And that's why controlling entropy controls your heat flow, and that controls your energy to some extent. We said that free energy is just a combination of real energy, and it also accounts for how much energy you can get out of your environment using entropy to control the heat flow. And so free energy tells you what's really available to do useful work. And a better term for free energy would be available energy, because free energy sounds like you're getting something for nothing, which you're not. But available energy just tells you how much energy is available to do useful work, including the energy you've already got in your system, plus any energy you might be able to get thermally from the environment. So that's all free energy does. It's just an accounting thing, so you can keep track of what you've got available to you. So we can make an analogy. Free energy is like a balance sheet. Free energy takes into account how much energy you've actually got and how much energy you're owed by the environment. And now it could be, though, that the environment doesn't owe you energy. It could be that you owe the environment energy, and free energy takes that into account as well. If you owe the environment energy, then your free energy takes the amount of energy you've actually got, subtracts off what you owe, and what's left is what you have available to do useful work. It's just a balance sheet. That's all. And then finally, what we said is, when do we waste the opportunity to do work? And that happens whenever the net entropy of your system plus the environment goes up. Anytime the net entropy of your system plus environment goes up, you have wasted an opportunity to do work, or at least lost an opportunity to
when I'm just trading entropy, the internal and the external environment, I haven't lost anything. But when I increase the overall entropy, I've wasted energy.
Right. And that's related to the concept of reversibility. If the net entropy has not changed, then you can reverse whatever process you just did and go back to your initial state. So you've lost nothing. But if your net entropy has gone up, it's never going to go down, because the entropy of an isolated system can only go one way. It can stay the same, or it can go up, but it can't go down. So once it goes up, you have lost some opportunity for doing useful work. And so that's the sort of the simple intuitive measure you can use. And when you're looking at a system, you can tell pretty quickly whether the net entropy went up or not. And if it did, you lost some opportunity to do work.
The overall entropy has to go up, but within a confined system, particularly a system where I add energy, I obviously can have entropy go down. I can reduce the entropy by building a car. Exactly.
And actually, that takes us to another point that we should be clear on. sometimes people say the entropy of any system goes up. And that's clearly not true. If I put a glass of hot water on the table, that water will cool down. It will lose energy and it will lose entropy. So clearly the entropy of a hot glass of water does not go up spontaneously. It goes down. So sometimes people say, well, okay, so a system maybe doesn't go to maximum entropy, but it'll go to minimum energy. But that's not true either, because if I put a glass of cold water on the desk, the cold water is going to warm up. Its energy is going to go up. So clearly a system does not necessarily spontaneously evolve to maximum entropy, nor does it spontaneously evolve to minimum energy. Neither of those is true. We hear that all the time. All systems evolve to maximum entropy. No, they don't. All systems evolve to minimum energy. No, they don't. So we could ask, so what do they evolve to? And it turns out that this same quantity, free energy, that we use as our balance sheet to keep track of how much work we have the ability to do, that quantity is the quantity of a system that is minimized at equilibrium. So systems spontaneously evolve to the state of minimum free energy, not to the state of minimum energy. And those are very different things. That brings us to the shake test, which this is something I teach my students, which is how can we get a sense of whether a system that has constraints that satisfy certain properties has more or less entropy than a similar system with different constraints. And so the example I use is, suppose I have some flour and some sugar, and let's say all the particles are essentially the same size and mass, and I just sort of throw them into a container, and so they're still all blobby and they're largely unmixed. And then let's say I have another container with the same amount of flour and sugar, but it's all uniformly mixed together. And the question is, which one of those has higher entropy? And to even ask that question, we have to be careful and define our constraint. Any single static system that isn't swirling around, entropy is not defined. So what I can do is I can say, what is the entropy of a system where I've just taken a cup of flour and dumped it in and a cup of sugar and dumped it in? That's a condition of a system. And if I do that twice, I'm not going to get exactly the same distribution of flour and sugar. So there is variability there. And that means I can define an entropy for that. And then the uniformly mixed thing, I have to be precise in my definition. What does it mean to be uniformly mixed? And what I can say is that for any given particle of flour, there's another particle of flour close by within, say, 5 grains, or similarly for the sugar, or some kind of constraint like that that says they can't be too isolated, or for every particle of flour, there has to be a particle of sugar within 5 grains of it. And that is an unambiguous definition, and therefore I can assign an entropy to that. So let's say I've made those definitions. Now, which has more entropy, the one where I've just thrown the flour in, or the one where it's all almost uniformly mixed? Well, aesthetically, if we tried to view this as disorder, some people look at the clean separation of flour and sugar, and they say, oh, that's very orderly. So that's a low entropy system. But other people would look at that and say, oh, it's all blobby and gooey, and there's blobs of flour and blobs of sugar. That looks very disorderly to me. And so I'm going to say that has high entropy because it's disordered. And that person might look at the more uniform mixture and say, oh, that looks nice and neat. It's very ordered and clean. It's all uniform. And they say, therefore, I'm going to guess that the blobby mixture has high entropy and the uniform mixture has low entropy. And so they have reached exactly the wrong conclusion, exactly the opposite. And that's because orderliness is a human aesthetic. And it's not a precise thing that we can define. And aesthetics are likely to mislead you. Instead, if we use what I think is a better visualization of entropy as uniformity, then it's pretty clear that the uniformity of the particles distributed throughout the mixture is much more uniform in the case where they're nearly uniformly mixed. And that's uniformity is entropy. That's the higher entropy state, and that's the correct visualization for it. We can use what I call the shake test to assess which of my flour and sugar containers has higher or lower entropy. And the way the shake test works is you pick up the container and you shake it vigorously, and then you set it back down. And the question is, I have these two systems. If I pick them both up, shake them both, and set them back down, then which one starts to look like the other? And the one that starts to look like the other is the one that started in the low entropy configuration. And by shaking it, I made it spontaneously evolve to higher entropy. And so the shake test allows you to determine which one had more or less entropy. You can just, like as a thought experiment, you can figure it out just by thinking about it. Clearly, if I shake up the blobby mixture of flour and sugar, it's not going to stay blobby and it's not going to become more separated. It's going to approach the uniform mixture of flour and sugar. If I shake the uniform mixture, it's not going to separate into a blobby mixture. And that tells me the blobby mixture was the low entropy one and the uniform mixture was the high entropy one. But crucial to the shake test is that all other factors, and in particular, all other energies, have to be exactly equal. So when I shake this blobby mixture, I had to have started, first of all, with a mixture that had a flat top on it. And my other container has the same number of particles with the same flat top. They have exactly the same gravitational potential energy. And when I shake them and let them settle down and smooth out their tops, they again have exactly the same gravitational potential energy as they did before shaking. So shaking is like adding heat. Heat is random energy.
Yes.
Shake it, I'm adding random energy. And then once I let it settle down, that's just so I can sort of take a look at it and make an assessment of it. But if there's an energy difference before and after shaking, then the shake test is not valid. And so, for example, if you have a bunch of nails in a container and they're all stacked randomly on top of each other, if you shake that container, those nails may settle down and line up and now become much more uniformly arranged than they were. And that's not higher entropy, that's lower entropy. And the only reason that happens is because there was a great decrease in gravitational potential energy as they sorted themselves out and settled down. And what that tells you is the free energy of the system was higher before you shook it, and the free energy of the system was minimized when you shook it. But that free energy takes into account not only the decrease of entropy that happened, but the significant decrease in gravitational potential energy that happened. So if the energy is changing, then you're no longer looking at just entropy. You're looking at a combination of energy and entropy. And you can't make a simple judgment anymore.
Alrighty then. Through the magic of poor video editing and me being a complete novice, we've reached sort of an abrupt end. And rather than drag Eric back into this, I'll just sign off and thank him for being so generous with his time and being so helpful, not only for this video, but anytime I call him to talk about topics like this. He and I both had a lot of fun making this, so despite having a really tiny audience, I think I'll make more and certainly have him join me when possible. Thanks very much.